Hello, this is Archer Murray, and this is my video presentation on the Hill Cipher and linear algebra. So in this presentation, first I'm going to give you an introduction to cryptography and the Hill Cipher. Then I'm going to walk through how to perform the Hill Cipher, and then I'll explain the usefulness of the Hill Cipher and its relevance to linear algebra. So first, I suppose I should give you an introduction. Cryptography is the study of keeping information secure by encrypting it. Cryptographic techniques are generally designed to avoid what's called cryptanalysis, which is when you can reverse encryption in order to recover the original message. A cipher is an algorithm that encrypts a message by changing its letters or letter groups. The output of a cipher will generally be a seemingly random string of characters. Ciphers should generally be easy to use while being resistant to cryptanalysis. The plain text is the original message before it's been encrypted. The ciphertext is the message after it's been encrypted. And a key is a value you can use in a cipher in order to make that particular usage of the cipher unique. So if someone intercepts your ciphertext, then even if they know the cipher that's been used, it'll be useless if they don't know the key. The Hill cipher is a cipher that was invented by Lester S. Hill in 1929, and it uses matrix multiplication to change groups of letters in a message. Now I'm going to walk you through how to perform the Hill cipher. So our plain text is going to be linear algebra, and our key is going to be math 3320. And after we find the ciphertext, we are going to decrypt it in order to recover the plain text. So first, here is our key and our plain text. Now, we're going to be plugging both of these into matrices. However, we can't plug letters into matrices. We can only plug in numbers. So we need a way to convert these letters into numbers. Here is an alphabet that does that. So we can see 0 gets converted to 0. The numbers stay the same. A gets converted to 10, B to 11, C to 12, and so on. And also some punctuation and special characters. Notice that this alphabet has 41 characters, a prime number. It's important to have a prime number of characters for a reason I'm going to get to later. So we use our alphabet to convert the key and the plain text. And then we plug the values into matrices. So watch carefully. So you may have noticed there that the key values get plugged into the matrix from left to right and then from top to bottom. However, the plain text values get plugged into the matrix from top to bottom and then left to right. So I'm going to play this animation again and watch and see how the values get plugged in different directions each time. Now, the key has to go into a square matrix because the matrix has to be invertible for decryption to be possible. And in this case, the key has just enough characters to fit into a 3x3 matrix. If there weren't enough characters to fit into a square matrix, then we would pad out the remaining values in the matrix with 1, 2, 3, 4, and so on. Now, the message matrix has to contain the same number of rows as the key matrix. This is so that matrix multiplication is possible. Now, you'll notice this time, our plain text is only 14 characters, which is not a multiple of 3. So we'll pad out that message matrix with a space, which is 40 in our alphabet. Now, in order to find the ciphertext, we multiply the two matrices, and we get this matrix with a bunch of really big values. Now, there are only 41 characters in our alphabet. However, these values are way more than 41. However, we can easily get these values into the 0 to 40 range that we need using the modulo operator. So this gray matrix is equivalent to this yellow matrix, mod 41. If you're not familiar with the modulo operator, it's basically finding the remainder of a division. So take 99 in the bottom left there. 99 divided by 41 is 2 remainder 17. So 99 mod 41 is 17. Useful thing about mod is that the output of mod 41, for instance, will always be between 0 and 40. So we read the values of this ciphertext matrix from top to bottom and then left to right, just like we did with our plaintext matrix. And we use the alphabet to find our ciphertext, which is h2mlv.hw4z9.j. Now we are going to decrypt this ciphertext and recover our plaintext. Now, first we need to convert this back into numbers. Now, remember how we multiplied the plaintext matrix by the key matrix to find the ciphertext matrix? Well, it seems sensible to say that if we multiply the ciphertext matrix by the inverse of the key matrix, we'll recover the plaintext matrix. Now, finding an inverse within a modulus is kind of tricky. You can use the same row reduction of an augmented matrix in order to find the inverse of a matrix in a modulus. However, we have to make some slight modifications to our row changing operations to account for the fact that it's a modular inverse. Now, this is quite tedious to perform by hand, so I'm just going to skip to the result, which is this matrix. Now, we can verify that this is correct by multiplying the two matrices like this, and then doing the mod 41, and sure enough, we get the identity. So we can say the green matrix is the inverse of the cyan matrix mod 41. So now that we have our inverse key, we multiply it by the ciphertext matrix, and we obtain this big matrix, which we then use mod on in order to recover our plaintext matrix. And just to make sure, the plaintext is linear algebra with a trailing space that we can ignore. So that's how you perform the Hill cipher. Now, how useful is it? Now, I've already established the Hill cipher is quite difficult to use by hand because you have to convert a modular matrix inverse. And if the message is really long, performing matrix multiplication can be kind of tedious. In addition to the difficulty of using the Hill cipher by hand, Hill cipher is also susceptible to cryptanalysis. So you see the highlighted rows in these matrices here? Well, the top row of the green matrix is the only row that determines the highlighted characters in the plain text. You can verify this with if you know a little bit about matrix multiplication. So what you can do is, if the message is long enough, you can try a bunch of possible values for just this row of the inverse key matrix, and keep trying values until you get a row that results in the highlighted characters of the plain text matching the character distribution of the English language. So a lot of E's and T's and other common letters. So the Hill cipher isn't that useful in real applications, but it is still relevant in linear algebra. Consider this: computing a modular matrix inverse is quite tedious. Wouldn't it be nice if we had a matrix that was its own inverse? Well, this is an example of such a matrix, an involutory matrix. You can see here this matrix, as you can see, when we multiply them, we get the identity mod 41, which means that they are inverses of each other. And since the two matrices are the same, we can say that this matrix is involutory mod 41. But just how common are involutory matrices? Well, you can see for the most part, it increases as your modulus increases, but it doesn't always increase. Prime moduli have fewer involutory matrices than composite moduli, but for all moduli, the number of involutory matrices, as you're about to see, is much lower than the total number of matrices. So if an attacker knew that you were using an involutory matrix to perform this cipher, then they could do a brute force attack much more feasibly than if you were just using any old matrix. But you can't just use any old matrix in this cipher because the matrix has to be invertible for decryption to work. So how many invertible matrices are there? Well, this is a graph of the percentage of matrices for a given modulus that are invertible, shown with the black circles, and the gray triangles indicate the percentage that are involutory. You can see for any sufficiently large modulus, there are almost no involutory matrices. Now, you'll notice looking at this graph that prime moduli have a much higher percentage of matrices that are invertible than composite moduli. So if you want to maximize the chance that any random matrix you select will be invertible and therefore usable for this cipher, then you should use a prime modulus. And that's why we had our alphabet contain a prime number of characters earlier. So in conclusion, the Hill cipher is less than ideal for practical use. However, it is nonetheless relevant in linear algebra. The combination of linear algebra and modular arithmetic in the cipher process leads to interesting consequences, like the invertibility of a matrix within a modulus being heavily dependent on the prime factors of the modulus, and the much increased presence of involutory matrices compared to matrices that are involutory for real numbers. And that is the end of the presentation.